Hi, good afternoon, guys, and we are here with our last lecture of the year, and we're going to be focusing on the history of the Earth. If we had been in the class, we probably would have done a whole unit on the history of the Earth and talking about how things have changed in the Earth over time. But because we just kind of want to talk to you about something you're going to be looking at next year in biology, and that's when you start getting into evolution and natural selection, is how do we know how old something is on the Earth? And so we're going to look at the evidence of the history of the Earth by talking about radioactive dating today and what that is, and then you're going to do a lab about it. So today our objective is to learn a little bit about radioactive dating and how we use that to determine the age of things on Earth, including how old the Earth is. All right, so one of the things that we have is evidence of past life on the Earth, and we call those fossils. So when we've talked about fossils, we know that they are the solidified remains or imprints, so maybe it might not necessarily be the actual bones and things. It might be casts of them that we see, like that they've left an impression, like their footprint, or maybe the shell imprints that we see in rock, and they are of once living organisms. What we do know is that the older a fossil is, the further down in the rock layers it is. So the further you go down, the longer it's been dead, the longer it's been there. So we know that those fossils on the bottom are older than the ones at the top. We also know that organisms that resemble some of the living creatures of today are mostly going to be found in those top layers. So we look for connections that way, while more of the much older ones and where we look for changes are found in the lower rock layers. So one of the very interesting things as we find is that 99% of all organisms that ever lived on the Earth are actually extinct. And whether that's because of climate change, which we just got done talking about, their climates change so drastically, or because of things like succession, where the environment changes, and so they actually their environment changes so much they can no longer live there, or if it's because of human interference, things like that. We do know that thanks to the fossil record, we can see that most things that used to be on the planet are no longer here, and that's usually we can look at that and try to figure out what happened. And so fossils provide what's called a historical sequence of life known as the geological time scale. And like I said, if we had been in the classroom, we would have gone more into this. Today, we're just going to kind of focus on how do we date things? How do we know how old they are? All right, so how do we estimate the age of a fossil? We use something called radioactive dating. And radioactive dating, as you can see in this little animation that's going on here, what happens is when something dies, it starts to decompose and it breaks down. And what we know about it is that the carbon inside of these organisms break down into something else. And so we can actually look and see how much carbon does something have left to kind of give us an idea. And so what we know about rocks is that rocks contain radioactive chemicals that break down. You saw in that animation, it started as carbon and it broke down into nitrogen. We use a term called half-life. Half-life is the amount of time it takes for half of the chemicals in a rock to decay or turn into another chemical. So here we saw that the carbon decayed into nitrogen. And that's because it releases its ions, and you can see in the periodic table that nitrogen comes before carbon. And so half-life simply is the time it takes for half of it to go away. That's why it's called half-life. So what we do is we analyze a sample of the radioactive chemical from a rock found near a fossil, and then we calculate its half-life to estimate about how old the fossil is. So we find fossils, and then we look at the rocks near them. And the rocks near those fossils, we see, well, how much of what do they have left in them? We calculate its half-life. And then that gives us a really good idea that, hey, probably the fossil that was right next to that rock is the same age. So different chemicals have different half-lives. So we're going to focus mostly on carbon, but sometimes for the history nowadays with living things, but in the history of Earth, we look at things like uranium becomes very useful, as does plutonium. For our example, we're mostly going to focus here on carbon-14. Carbon-14 is a radioactive isotope, meaning it has more neutrons than regular carbon would have. And that means it's unstable. And now as you get into chemistry, your junior year, we're going to learn that elements all want to be stable. So they're working their way to becoming stable. And so as carbon-14 decays, its atoms change into something more stable, nitrogen. And we know how long it takes. For carbon to become nitrogen, it takes about 5,700 years for half of the radioactive atoms to change. So it's going to take half of carbon-14, for half of it to switch, to turn into nitrogen-14, 5,700 years. So that's what's referred to as its half-life. So the period of time known as the half-life of carbon-14 is 5,700 years. And then you can see over here, uranium has a half-life of 713 billion years. You're going to have plutonium has 2,400,000 years. I'm sorry, I was wrong here. This is 713 million. This is 13.9 billion. Sorry, it's 713 million, and this one was 2.4 million years. So you can see whereas uranium and plutonium would be much more useful looking at things that are much older than like carbon, which should be 5,700 years. So what we do know is that all living things contain carbon-14. We know that plants take in carbon dioxide during photosynthesis. We talked about that in our last unit when we looked at the carbon cycle, and therefore all animals take in, so carbon dioxide during photosynthesis, therefore also take in carbon-14. So we know plants take in carbon-14. Well, then anything that eats plants, us, other animals, we take in carbon-14. So all living things have carbon-14. Whether it's the plant that makes it or whether it's because an animal or human ate a plant, we get our carbon-14. So when a plant or animal dies, we're no longer taking in carbon, right? We're not doing photosynthesis if you're a plant. You're not eating things if you're an animal because you're dead. So the minute that happens, the carbon begins to change, decay into nitrogen. And after a while, most of the carbon-14 will decay into nitrogen-14. All right, so let's kind of look at this. So on your notes in front of you, you should have a picture of 6 boxes. It's going to look something like this. You're not going to have the dots in it. And so what I would like for you to do is in box 0, I want you to draw 100 dots. Okay, so if you need to, pause the video here, take a minute, pause me, draw 100 dots. All right, so in box 0, you should have 100 dots. This represents the amount of C4 in the sample right when it died. We're going to start death at 0. So we know that the half-life of carbon-14 is 5,700 years. So after 5,700 years, how many dots do you think should be in box 1? Remember, half of the carbon is going to change into something else. So if you start with 100 dots, half of 100 would be 50. So in box number 1, you should put 50 dots. So we're going to see here that we're going from when it died, 100 dots, to 1 half-life, which was 5,700 years later, to 50 dots. All right, so what would happen if we did another half-life? So let's say we had another 5,700 years pass. Would all your dots just disappear? How many dots would you have in box number 2? They wouldn't all just disappear yet, right? Because now we have 50, so what's half of 50? You would have 25 dots remain. So what I'd like for you to do here is put your 25 dots, just like I did in mine, in box number 2. So over here, you have the 25 dots. And then I want you to finish it out. Go another 5,700 years. How many would you have to after 3 half-lives? So now you're starting with 25. You have to ask yourself, what's half of 25? And then what about after 4 half-lives? Another 5,700 years, how many would you have left? And then after a 5th half-life, another 5,700 years pass, how many would you have? So finish filling that out, and you're going to notice that each half-life we get, remember we started with 100, you're going to end up with very, very few left. So after you have 5,700 years past, box 3, how much would you have left? So we started with in box 2 with 25. So how many would you have left? You have 12 and a half dots. Just do your best with the half dots. I just put 12 in mine. If something died 5,700 years ago, how much of a percentage is left? So if we started from today and we said, okay, 5,700 years ago, how much would be left? Half of it, right? Because 1 half-life, 50%, is 5,700 years. So what if we doubled that? What if we did 11,000 years? Something, if it's been dead for 11,400 years. So that's 2 half-lives. So we're going to go from 100% to 50. That would be 1 half-life. 50 to 25. Very good. And then what if we added one more? What if we said it was 17,100 years ago that something died? How much of the sample would be left? Well, you would go from 100 to 50 to 20, 25 to 12.5%. Good. So using boxes 0 through 5 above, how many total years have passed? So if we look, remember, each half-life is 5,700 years. So from 0 to 1 was 5,700, 1 to 2 was 5,700, 2 to 3 was 5,700, 3 to 4 was 5,700 years, and then 4 to 5 was 5,700 years. That's 5 half-lives. So it'd be 5 times 5,700, which would be that whatever this was died 28,500 years ago. So what would be the amount left if another? So say we went from box 5 to 6. We'd only have about 1.5% of our sample left. So what happens when it becomes too small? Notice after a while it becomes so small that we can barely see it anymore. This is at the point which carbon dating is no longer useful. So this is why we have to use those other elements that we talked about back in the beginning. We have to find things with longer half-lives because we need to have numbers that are greater. We're going to run out of carbon. At least you're not ever going to truly run out of it, but we're not going to be able to find enough in the sample to test. So this is where we start using uranium. So we use that for our larger numbers. For example, if you have an initial sample of 8 grams of radioactive material, after 7 half-lives, only 0.125 grams of the sample would remain. But it's still enough to measure around the 4.9 million years. Thorium's half-life is too long, and plutonium's half-life is limited. It might help with some things, but it wouldn't help with all of them. All right, so the initial amount of uranium in a sample is 227. A rock that's 16 grams, and the half-life of it is 3,400 years. So uranium-227, that's just as a atomic number. We know that in a sample of rock is 16 grams. And the half-life is 3,400 years. How much time has passed if there's 2 grams? So we need to know how many half-lives does it take to get to 2. So we started with 16. After 1 half-life, you would have 8. After 2 half-lives, you would have 4. After 4, and then after a 3rd half-life, you would have 2. So this would be 3 half-lives. So 3 half-lives, and that each half-life is 3,400 years. We would take 3,400 times 3. And it would be 10,200 years have passed since this organism died. All right, so we're gonna focus some more on radioactive dating. So we're gonna do a radioactive dating game. The link to the virtual lab is on Canvas, as is the actual document. You can find them both there. So I'm going to show you your document. The document looks like this. And you're going to see there's one on half-life, decay rates, and measurement, and then the actual dating game. So this is what you're going to complete for me. Your directions are right here. I'm going to take you to the site. Let me try to share this right. Okay, show me there. All right, so for the first one, it says for you to click the pause button. So make sure on here you click pause down here. See right now, if I clicked it, I press play. Here's pause. All right, and then just follow your directions. You'll notice that up here, we're in the half-life. Here's your half-life, decay rates, measurement, and dating game. Those are all your tabs at the top. And here it says add 10. Click the add 10 button below the bucket of atoms repeatedly until there's no atoms left in the bucket. We'll go back here and I'm going to click, see how it's a plus 10. I'm going to click it until there's no more atoms inside the bucket. It says there are now 100 carbon-14 atoms on the screen. The half-life of carbon is about 5,700 years. We talked about that. If you left those 100 carbon-14 atoms sit for around 5,700 years, how many would you expect to decay? So if you let 100 atoms sit for one half-life, how many do you think you'll have left? Well, my prediction would be about 50. That's a half. Like, remember, half-life means the time it takes for half of it to disappear. So now we're going to click back here, play, and we're going to stop it or try our best to stop it near this half-life line. So watch at the top. When that red one hits there, pause it close, and we'll see. Yeah, here I'm not quite there because I'm not perfect, and that's okay. But I'm at 43. So was I pretty close? Yeah. Then you're going to reset it all and do it again and see how you get there. And so then you'll answer your questions. For B, you're just going to click on the decay rates and do the same thing. Read your directions here and then fill out your answers over here and do that same thing, measurement. Click on it. Follow the directions it says here. And then the dating game, same thing. Click here and do the ones that are there for you. When this is done, you submit it in, and this is our last assignment for us. And this will be due on Tuesday, May 12th at 11 p.m. Also note that on Tuesday, we are going to be having a live session during our actual class time around 10:40 to meet for our last time just to check out. So keep that in mind that you need to plan on Tuesday around 10:40 signing on to Zoom so that we can all have one whole class together on our last day. Then on May 13th, Wednesday, you are turning in your devices and everything back to the school. So be looking on the lookout for more emails about that. So hope you guys have a great summer, and I'll be checking out with you soon.